Welcome to this explainer. Today, we are covering Physical Science Unit 01, Lesson 08, Collision Design Challenge. We're going to take a magnifying glass to the exact forces that happen during a crash, and more importantly, figure out how we can use science to engineer our way out of disaster. Let's jump right in. Okay, picture this. You've got a tiny, high-speed meteor hurtling through the vacuum of space, right? And smack, it strikes a massive, heavily armored spacecraft. Now, that seems like a total mismatch. How could something literally that minuscule cause catastrophic damage to a multi-billion-dollar, super fortified structure? Just kind of hold that thought in the back of your mind for a second. To bring this back down to Earth, let's look at a second, much more relatable example. Imagine a massive semi-truck colliding head-on with a small, compact car. Instinctively, you just know the small car is going to get absolutely crushed. But why? I mean, is the truck actually pushing harder on the car than the car is pushing on the truck? We really need to build up this mystery before we reveal the one absolute physics rule that governs both of these crashes. And here is that golden rule, Newton's third law of motion. This law dictates that interaction forces occur simultaneously as an equal strength, opposite direction pair on two different objects. Let that sink in for a second, because this is huge. It means that when that massive truck hits the tiny car hits the truck with the exact same amount of force. It is always an equal strength, opposite direction pair on two different objects. No exceptions. There's literally no way around it. So let's test this out with a level A knowledge check. This one's for you. If object A pushes object B with 100 newtons of force to the right, what is the force on object A? Think about it for a second based on what we just learned. Okay, if you said object B pushes object A with exactly 100 newtons of force to the left, you absolutely nailed it. Equal strength, opposite direction. Boom. Now let's level up. For our level B check, we are going back to our space mystery. Why does a small meteor damage a massive spacecraft during a collision? Well, applying Newton's third law, the meteor and the spacecraft experience the exact same interaction force. They are an interaction pair. The difference isn't the force itself, it's how the object's physical structures handle that force. So the tiny meteor might completely vaporize under the stress, while the spacecraft takes severe localized damage, but they are both reacting to the exact same amount of force. Crazy, right? Since we can never ever change that equal and opposite force rule, we have to engineer around it. So how do we actually survive crashes? Number 1, increase stopping time. Number 2, decrease peak collision force. And number 3, manage that equal and opposite force. Think about dropping your cell phone when it has a thick compressible case on it. That squishy case works exactly like a car bumper. By crushing and compressing upon impact, it actually increases the stopping time of the collision. Because the crash takes slightly longer to happen, you dramatically decrease the peak force on the phone itself, even while that interaction pair with the floor remains perfectly equal. Which brings us directly to our engineering application. Here is your mission. You need to build a toy car bumper to protect a highly fragile payload that is crashing into a solid wall. We're taking the physics we just verified and using it to engineer a life-saving solution on a miniature scale. Of course, every good mission has rules. The crucial point here is setting up our criteria and constraints so we have a completely fair and safe way to evaluate our engineering designs. The rules are strict. You gotta protect the payload. You have to keep the bumper securely attached to the car during the impact. You're only allowed to use limited, specified materials within a certain size limit. And crucially, every single design must be tested under the exact same collision conditions. To test under those exact conditions, we need absolute scientific rigor, and that means strictly defining our variables. Our independent variable, the one thing we are purposely changing, is the bumper design. Our dependent variables, the things we're actually measuring, are peak force, stopping time, and payload damage. And finally, our controlled variables. These are the things we keep exactly the same to ensure a fair test, and they include the car's mass, the payload itself, the ramp height or launch speed, the wall, the starting point, and the number of trials. If we change the ramp height halfway through testing, our data's totally useless. When we run repeated trials, the collision evidence becomes crystal clear. Just look at the force versus time data comparing different designs. When we tested a rigid plastic bumper, the stopping time was a lightning-fast 0.1 seconds. That resulted in a massive peak force of 50 newtons and, no surprise, high damage to our payload. But check out the foam block bumper. The stopping time stretched out to 0.4 seconds. And because we increased the time, the peak force plummeted to just 15 newtons, and the payload suffered zero damage. It's a total game changer. Let's use that data to build out a claim, evidence, reasoning conclusion. This models exactly how to justify one design over another using our trial data. Step 1, the claim. The foam block is the better bumper. Step 2, the evidence from our trials. The peak force dropped from 50 newtons down to 15 newtons, and stopping time increased to 0.4 seconds. Step 3, the reasoning tying it all together. According to collision physics, the foam increased the stopping time, which successfully reduced the peak force on the payload, even though that equal and opposite interaction force still existed between the bumper and the wall.
All right, now it is your turn. Here is the final challenge. I want you to sketch an improved toy car bumper. Combine materials if you have to. Then justify your design using your CER skills. Use the criteria, the constraints, all those controlled variables we just discussed, and our trial data to prove exactly why your new design is scientifically superior.
To wrap up this explainer, I've got a quick question for both parents and students listening. How will your next engineering design handle that inevitable equal and opposite force? Because understanding this isn't just about toy cars in a classroom. This is the exact same foundational physics used by real-world automotive engineers to design crumple zones that literally save lives every single day. The universe is always going to give you an equal and opposite force. The question is, how will you engineer your way through it?